In PV1X, we have discussed that light can exist in the familiar form of photons or in the form of plasmons propagating at the surface of a metal such as gold, silver, copper or aluminum. Localized surface plasmons can be excited on metal nanoparticles. This figure illustrates an incident photon exciting a plasmon at the surface of a silver nanoparticle. The black lines, which indicate the flow of energy, show that the energy gets very much concentrated near the surface of the particle. According to the meteor, small particles of about 10 nanometers convert nearly all the incident energy to heat, while particles larger than 100 nanometers re-radiate most of the energy and form very efficient light scattering elements. In PV1X, we have shown that the plasmon resonance wavelength at which this occurs can be tuned throughout the visible and near-infrared part of the spectrum. This plasmonic effect has been used for centuries to color glass, and nowadays it's well understood and also used in optical biosensors and other applications. The objective of this video lectures on plasmonics is to discuss whether plasmonic effects can be useful for solar cell applications as well. The conventional view is that plasmons should be avoided because they are loss mechanisms. For example, it is well known that a rough metal back reflector is less reflective because of plasmonic losses. However, in the 90s, Stewart and Hall showed that plasmons can be beneficial as well. They put silver nanoparticles of about 100 nanometers at the front of a very simple crystalline silicon photodetector and enhanced its sensitivity at a particular wavelength by almost a factor 20. This attracted the attention of the PV community, and various approaches for the integration of plasmonic structures in solar cells were investigated. In their 2010 review paper, Atwater and Pullman summarized the approaches into 3 categories. Using silver nanoparticles at the front of the absorber layer to couple light into the layer and trap it inside. Using a silver nanoparticle inside the absorber layer to enhance the absorption in the near field. And using silver nanoparticles behind the absorber layer to backscatter the light into the so-called guided modes. This review of Atwater and Pullman is very optimistic and suggests that the incorporation of metal nanoparticles could revolutionize high-efficiency PV device designs. But is this optimistic view supported by experimental evidence? Therefore, in this video lectures on plasmonics, I would like to address the following questions and learning objective. Can these plasmonic light trapping approaches really be useful for solar cell applications? And here I don't mean useful for enhancing photodetectors or low efficiency devices in a limited spectral range, but really useful for enhancing the efficiency of state-of-the-art solar cells. In this lecture, I will systematically go through these configurations with silver nanoparticles at the front, inside or behind the absorber layer. In each case, I will check how well the nanoparticles function compared to more conventional approaches when it comes to anti-reflection, light trapping, concentration and scattering. In this lecture, I will focus on the metal with the most suitable optical properties, and that's of course silver in combination with the most commonly used absorber material, silicon. And I will consider both the crystalline silicon and the thin film silicon solar cells. Let's start with nanoparticles in front of the absorber. In such a configuration, the nanoparticles serve 2 purposes. The first is anti-reflection. As discussed in PV1X, the reflection from a bare crystalline silicon wafer is very high, and it has been demonstrated that it can be reduced by covering the surface with an array of plasmonic silver nanoparticles. It is fascinating to see that a reflective metal like silver can have an anti-reflective property. These properties depend on the diameter, the height of the nanoparticles and the distance between them. Spinelli systematically varied all the parameters and found that in the best case, the absorption in crystalline silicon is enhanced by 35%. This seems to be very promising. However, the conventional approach of using an anti-reflective coating of silicon nitride, which is much cheaper and simpler, enhances the current by 41%. So it's unlikely that silver nanoparticles will in practice be used for its anti-reflective properties. The second purpose is light trapping, keeping the light that tries to escape the wafer inside until it's fully absorbed. It's often claimed that nanoparticles on the surface can do this because they preferentially scatter the light towards the side of the high refractive index. So that means back into the crystalline silicon wafer. However, an electroluminescence measurement by Catchpole clearly shows that the photons generated inside a crystalline silicon LED escape more easily from the part of the device that is covered with the silver nanoparticles in reference to the part not covered with the silver nanoparticles. So this proves that there is no trapping effect from the silver nanoparticles, but that the opposite is true. Light is coupled out of the crystalline silicon wafer. The next approach is to put the plasmonic nanoparticles inside the absorber layer. The idea here is that the silver nanoparticles concentrate the light in the near field and enhance the absorption locally. The first issue with this approach is the absorption loss in the metal. Because the metal has a much higher absorption coefficient than the semiconductor, the absorption loss in the metal is always much higher than the useful absorption in the silicon. A second issue is that when the energy is concentrated near the surface, there is less energy and less absorption further away from the particle. In most devices, this cancels any absorption enhancement in the near field. Then there are also some practical issues. The absorption is enhanced mostly within a few nanometers from the metal surface, which implies that the metal and semiconductor should be in contact. However, this creates a silver-silicon interface at which photo-generated charge carriers can recombine. When we fabricated thin-film silicon solar cells with silver nanoparticles embedded inside the absorber layer here at the Delft University of Technology, we found that both the current, voltage and fill factor dropped significantly. As a result, the efficiency of all devices was reduced by at least 50%. This demonstrates that this approach requires passivation of the metal surface, which in my opinion will be very challenging and complicated. The final possibility is to have the silver nanoparticles behind the absorber. This is the most promising approach, so I will treat this in a bit more detail. And I will do that in the next video lecture.